Welcome to the class. We have seen that how does the Brayton cycle work and how it is useful for aircraft propulsion. We have found out what is the optimum case in which a Brayton cycle should operate, and then what is corresponding network and efficiency. Then we have thought that we can improve the performance of the Brayton cycle by having certain attachment, and we have seen that there can be an attachment of heat exchanger and there can be also an attachment of reheater. So those attachments have their own advantages. Now we are going to see in today's class Brayton cycle with intercooler or Brayton cycle with intercooling. Here we will see what is the use of intercooler and how does Brayton cycle's operation changes, or how does Brayton cycle's operation change with the attachment of intercooler. We would also see the performance of Brayton cycle with all the attachments whatever we have considered. So let us start with Brayton cycle with intercooler. Now here we will first draw the schematic, and schematic says that there will be one compressor, and then this compressor would compress, but this is for us now the low pressure compressor. After the low pressure compressor, before going to high pressure compression, this air will get cooled and then it would enter into the high pressure compressor. This is high pressure compressor, and then there is cooling of this air using some coolant, and then this is what we are referring here as intercooler. Then from high pressure compressor, air will go into the combustion chamber, and from combustion chamber air will enter into the turbine. So here we will have state 1 here, state 2 here, state 3, state 4, state 5 and state 6. So as what we can see, in case of reheater we had 2 turbines and 1 compressor. In case of intercooler we have, with this schematic we have 2 compressors and we have 1 turbine. This is according to the present schematic. Then we can draw the thermodynamic cycle for the intercooling, and this cycle we will draw first for TS diagram, and as per TS diagram, state 1 to 2 is compression, which is isentropic. So we are at state 1 and state 2 is isentropic compression. Then state 2 to 3 is intercooler, and as what we know in Brayton cycle, other heat addition or heat rejection processes are isobaric. This is also an isobaric cooling. Since it is cooling, temperature will decrease, entropy will also decrease, and it can come to any temperature down, but we will refer it coming down to same temperature as 1. So the state is 3 temperature is equal to state 1 temperature. Then we will have 3 to 4 as high pressure compression. So we will have state 4 here. Then from state 4 to state 5 we have heat addition isobarically. Then 5 to 6 we have isentropic expansion, and 6 to 1 we have heat rejection. So this is the thermodynamic cycle with intercooling for Brayton cycle. Now we will see how PV diagram would be for the intercooling process in Brayton cycle. So here we have 1 to 2 as isentropic compression, and 2 to 3 is cooling isobaric. So this is 3, and practically we will have same temperature. This is isothermal line on the PV diagram, and 3 to 4 is this. We have we will see this is isothermal line, then this is 3 to 4 is isentropic compression, 4 to 5 is isobaric heat addition, 5 to 6 is isentropic expansion, and 6 to 1 is again isobaric heat rejection. So, here we have low pressure compressor, here we have high pressure compressor, here we have combustion chamber and turbine. Similarly, in the TS diagram, here we have low pressure compressor, here we have high pressure compressor, combustion chamber, turbine, and this is the place where we are having intercooler. Here we are having intercooler in 2 to 3. So, this is how we will have Brayton cycle diagram with the intercooler. Here, as what we can see, there is no alteration in the turbine work. Turbine work does not get altered so far as the temperature 5 is same without or with intercooling, the statistic 6 is same, then we will have same turbine work output. Intercooling just reduces the compressor work. So, mainly intercooling reduces compressor work and it does not alter the turbine work. So, in general W net increases with intercooling. So, we will see about it. Then for that, let us consider the heat and work interactions in the presence of intercooler. So, for that all sake, we will again draw TS diagram for the intercooler. T is on y axis and S is on x axis. So, for us 1 to 2 is isentropic compression, 2 to 3 is isobaric heat rejection in intercooler, 3 to 4 is isentropic compression, 4 to 5 is heat addition in combustion chamber isobaric, and 5 to 6 is expansion in turbine, 6 to 1 is again heat rejection. So, considering this, we can write down WC, which is compressor work, which is WC for low pressure compressor plus WC for high pressure compressor. So, we can know that WC for low pressure compressor it is H2 minus H1, and for high pressure compressor it is H4 minus H3. So, we can write down this H2 minus H1 as Cp into T2 minus T1 and H4 minus H3 as Cp into T4 minus T3. This is what we have compressor work. Then we can have turbine work, and turbine work is H5 minus H6, which is Cp into T5 minus T6. Q in is H5 minus H4, which is Cp into T5 minus T4. This is what we can write down. Then we can write down W net is equal to Wt minus Wc. So, for us W net is equal to Cp into T5 minus T6 minus Cp into T2 minus T1 plus Cp into T4 minus T3. Further, we can write down efficiency is equal to W net upon Q in. We know W net, we know Q in, we can find out the efficiency of Brayton cycle. So, this is how we can find out work and heat interactions and the performance for Brayton cycle with intercooler. But we have to argue with a point that we did stop intercooling at a state, and that state was 3 for us. So, we did compression in low pressure compressor from 1 to 2, and then we did intercooling from 2 to 3. So this state 3 at this moment is in argument, and we should find out what is this optimum location for state 3 such that we will have minimum compressor work. So we will try to find out what is the condition in which we can have minimum compressor work input such that we will have the point 3 accordingly chosen. So for us, we will again write down WC is equal to low pressure compressor work plus high pressure compressor work. So for us, WC is H2 minus H1 plus H4 minus H3, which is Cp into H2 minus H1. So T2 minus T1 plus Cp into T4 minus T3. So we have compressor work, we can take Cp common, it will become T2 minus T1 plus T4 minus T3. We can take T1 common here such that it will be Cp_T1, then it will be T2 by T1 minus 1 plus T4 by T1 minus T3 by T1. Again, let us consider here that T3 is equal to T1, and then we can get here WC is equal to Cp_T1 T2 upon T1 minus 1 plus T4 upon T1 minus 1, which is Cp into T2 by T1 minus 2 plus T4 by T1. Actually, pressure at 3 and pressure at 2 is same. So argument for state 3 is not upon temperature, it is upon pressure. So why did we stop for the pressure corresponding to 3, or why did we stop compression in the low pressure compressor at state 2? So we have to find out the best point 2 or point 3 for in the fact from the pressure, which will give us minimum compressor work. So let us say that the temperature ratio T1 is equal to T2 by T1. We are giving a new title as T1 for temperature ratio T2 by T1, and we know it is P2 by P1 bracket raised to gamma minus 1 upon gamma, and for all sake it is for us Rp1 bracket raised to gamma minus 1 upon gamma. Then let us say T2 is equal to T4 upon T3. We are saying this as T1 and this as T2, which is P4 upon P3 bracket raised to gamma minus 1 upon gamma, and for us it is Rp2 bracket raised to gamma minus 1 upon gamma. So let us find out what is T1 into T2. So it is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma into P4 upon P3 bracket raised to gamma minus 1 upon gamma. But we know here P2 is equal to P3, so it gives us P4 upon P1 bracket raised to gamma minus 1 upon gamma, and this is the cycle pressure ratio, which is Rp and bracket raised to gamma minus 1 upon gamma. So P4 by P1 is equal to P5 by P6 is equal to Rp. And then having known this we will say as, we will refer it as P4 by P1 bracket raised to gamma minus 1 upon gamma as T. and this gives us a fact that T1 into T2 is equal to T is equal to Rp raised to gamma minus 1 upon gamma. So we are having Wc is equal to Cp T1 into T1 minus 2 plus T2. Having said this, we will again write down this and find out Wc is equal to Cp T1, which is T1 plus T2 minus 2, but we know that T is equal to T1 T2 and T is equal to constant, since it is Rp raised to gamma minus 1 upon gamma, and we are having Rp is equal to constant. So we have Wc is equal to Cp T1 into T1 plus T upon T1 minus 2. So we will differentiate this with respect to T1 and equate it to 0. We will get accordingly as Cp T1, and differentiation of T1 is 1, minus Cp T1 into T divided by T1 square is equal to 0. So Cp T1 can get cancelled. So we will have T is equal to T1 square, and this leads to T1 is equal to square root of T. But we know T1 into T2 is equal to T. So we have basically T1 is equal to T2 is equal to square root of T, and this leads to the fact that Wc1, which is Wc low pressure compressor, is equal to Wc high pressure compressor. So both the compressors in optimum case should have same work input, and then we will have Wc is equal to Wc1 plus Wc2, which was Cp T1 into T1 plus T2 minus 2. So now it is Cp into 2 root T minus 2. So it is twice Cp T1 into square root of T minus 1. And for this we have Rp1 is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma. Rp2 is equal to P4 upon P3 bracket raised to gamma minus 1 upon gamma, and Rp1 is equal to Rp2, and this is equal to square root of Rp. So we have Rp1 is equal to square root of P4 by P1 bracket raised to gamma minus 1 upon gamma, and Rp2 also same. So this is how we can find out the optimum case, and then we will find out what is the optimum work, total work, and what is the corresponding efficiency. So for us Wc was Cp(T1) into 2 into square root of T minus 1, but then we will find out W net. It was Wt minus Wc, and now we can write down it as Cp into T5 minus T6 minus, there are two compressors, so we will have Cp into T2 minus T1 plus Cp T4 minus T3. So we can take W net as Cp T1 and everything can be T5 minus T6 minus T2. Okay, so this is by T1 and this is 1 plus T4 by T1 minus 1. Then this, for the optimum case, we can have W net is equal to Cp T1 into, as per the Brayton cycle, if we can try to plot, it was T on y axis, S on x axis. So we have 1 to 2 low pressure compressor, 2 to 3 intercooler, 3 to 4 high pressure compressor, 4 to 5 as heat addition, and then 5 to 6. Here T5 is equal to T max and T1 is equal to T3 is equal to T mean. So here we have T5 upon T1 is equal to T max upon T mean. So it is practically beta and this is known. So T5 upon T1 is beta minus T6 upon T5 into T5 upon T1, and this is minus T2 upon T1 is square root of Rp plus, here we should have minus sign and here it should have plus sign, plus 2 minus T4 upon T1, and this is again T4 upon T1 is Rp, square root of Rp. So we have W net is equal to Cp T1 into beta minus T5 T6 by T5 is equal to Rp into T5 by T1, sorry, this is T5 by T1 as beta and T6 by T5, which is T5 1 upon T5 by T6. So this is 1 upon Rp minus 2 square root of Rp plus 2. So the non-dimensional work W net upon Cp T1 is equal to beta minus beta upon Rp minus 2 into square root of Rp minus 1. So we practically would have this as beta into 1 minus 1 upon Rp minus 2 into square root of Rp minus 1, and then we can find out Q in is equal to Cp into T5 minus T4, which is Cp, we will take T1 common, so it is T5 by T1 minus T4 by T1. So T5 by T1 is beta, T4 by T1 is square root of Rp. So we will have now formula for efficiency as W net upon Q in, and this is for optimum case, which says that beta into 1 minus Rp minus 2 into square root of Rp minus 1. This is W net, and Cp, this is Cpt1 into beta minus square root of Rp, and Cpt1 gets cancelled. So we have beta into 1 minus 1 upon Rp minus 2 into square root of Rp minus 1 divided by beta minus square root of Rp. So, this is the formula for efficiency with intercooler for optimum case. Having said this, we can now find out how does efficiency vary with these cases, and for that we will see how does net work and efficiency vary with pressure ratio, as we have found out the relations for optimum case or for the pressure ratio variation. So, we have W net upon CPT1 on y axis and pressure ratio on x axis. So, this is a standard variation for a given beta 1 for the network. So, beta 2, so this is beta 3 and this is beta 4. Now, if we see efficiency, then this is efficiency with respect to pressure ratio, and efficiency would vary as this. Everything will start from Rp1. So, this is beta 1, this is beta 2, this is beta 3, this is beta 4, and beta is increasing in this direction. So, this is the variation of efficiency and network for the intercooler attachment of Brayton cycle. Now, let us consider if we have all the attachments in the Brayton cycles. Practically, we mean 3 attachments where we have intercooler, heat exchanger and then the reheater. So, schematic would be first we have one which is a low pressure compressor. So, this is a compressor and this is a low pressure compressor. From the low pressure compressor, air will go into the intercooler. So, we have intercooler attached along with the compressors. So, from low pressure compressor, air will go to the intercooler and then high pressure compressor. From high pressure compressor, air will enter into the heat exchanger. So, we will draw heat exchanger. This is air's entry into the heat exchanger, and then it will go into the combustion chamber. From the combustion chamber, air will enter into the first high pressure turbine. So, this is turbine and practically high pressure turbine. Then we will have it entered into the reheater. So, this is the arrangement for reheater where we will have heat addition. So, this is low pressure turbine, and from the low pressure turbine the exhaust will be sent into the heat exchanger, and then this is the heat exchanger which has entrance for the air from low pressure turbine and then also air from the high pressure compressor. So, suppose this is 1, this is 2, this is 3, this is 4, 5, 6, 7, we will have here, this is a reheater, this is 8, 9 and then 10. So we have such all arrangements. So now we can see what is the thermodynamic diagram cycle. So here we have T on y-axis and S entropy on x-axis. So 1 to 2 is low pressure compressor. So we have 1 to 2 low pressure compressor. Then it is going into the intercooler. So 2 to 3 is intercooler. 3 to 4 is high pressure compressor. After high pressure compressor, 5 to 6, 4 to 5 is is heat exchanger, and then 5 to 6 in the same pressure into the combustion chamber, then 6 to 7 into the turbine, 6 to 7 is into the high pressure turbine, and from high pressure turbine air is going into the reheater. So reheater process will take place till 8, and then we have 8 to 9 low pressure turbine, and then from 9 to 10 we have heat rejection into the heat exchanger, and 10 to 1 is heat rejection into the atmosphere for open cycle gas turbine power plant. So we have one here low pressure compressor, here we have intercooler, here we have high pressure compressor, it is heat exchanger for the air, this is combustion chamber, this is high pressure turbine, this is reheater, this is low pressure turbine, and this is heat exchanger for gas. So these are the different processes taking place into different components. Now we will plot PV diagram for this, and PV diagram says that we have 1 to 2 as isentropic compression, 2 to 3 as intercooling, 3 to 4 as high pressure compressor which is isentropic compression, 4 to 5 is heat exchanger isobaric heat addition, 5 to 6 is heat addition into the heat exchanger combustion chamber, then 6 to 7 is isentropic expansion in high pressure turbine, then 7 to 8 we have reheater, heat addition in the reheater which is isobaric, 8 to 9 we have low pressure expansion into the turbine, then 9 to 10 we have heat exchanger for gases, and then we have 10 to 1 as the process. 9 is here, this is 9, this is 10. So this is how we have thermodynamic cycle if we have Brayton cycle with all possible attachments. So for these attachments again we can see how does the net work output and net efficiency would vary. So this is the variation of net work output divided by CPT1, and then this is RP. It is simple over here to find out. We know here W net is equal to WT minus WC. So W net is equal to, there are two turbines, so we have WT high pressure turbine plus WT low pressure turbine minus, there are two compressors, so we have WC low pressure compressor plus WC high pressure compressor. So we need to add all the four works, all the two works for the turbine, and subtract all the two works from the compressor. So regarding Q in, we have two Q ins. One Q in is Q in into the heat exchanger we have Q in into the combustion chamber plus we have Q in into the reheater. So these two Q ins we should know. So efficiency then it is W net upon Q in. So there is external heat addition only in two processes. This is in the combustion chamber and this is in the reheater. So this, if we try to find out, and then we can find out what is the optimum case, but we will get same. For the reheating we will get a condition which states that both the turbines should do same work. If reheating is there, both the compressors will do same work. If intercooling is there, and then the temperature at the exit of the heat exchanger should be same as the temperature at the exit of the low pressure turbine. So these things whatever we have found out for the individual attachments would continue to be present for the complete set of attachments. So hence we can find out what is the variation of W net upon CPT1, and then this will vary with different betas. So this is for beta 1, beta 2, beta 3 and beta 4. As said, this is the increment of beta, and then we have efficiency calculated varying with pressure ratio. First we will find out efficiency, which is for no attachment case. This is efficiency for no attachment, and for no attachment further we have efficiency for different betas with each attachment. So this is efficiency for beta 2, this is efficiency for beta 3, and then we will get no attachment, and this is beta 1, and so we will have efficiency beta 1 here, efficiency beta 2 here, and this is efficiency beta 3 here. So this, there is no good idea to continue use of all attachments beyond this pressure ratio for beta 1, since it decreases the efficiency as in case of without any attachment. So with all attachments the efficiency is decreasing with beta 1 for beta 1 with increase in pressure ratio, but beyond this point it goes below the efficiency without attachment. So we can consider this efficiency variation for designing the Brayton cycle with different attachments. So this is how we will consider Brayton cycle for intercooling or considering Brayton cycle for different attachments. Thank you.